Hello guys, and today I'll be talking about chapter 2 of Campbell's Biology, the chemical context of life. And chapter 2 is the first chapter of unit 1 of Campbell's Biology, which talks about basic chemistry in correlation to biology. Now, I'm not going to be talking about the answered questions of this chapter because I want to leave it as an exercise for y'all to do on your own. If you want to check answers, then go on a website called Slater or simply check the appendix of the book. Now, let's first start off with the first term you need to know. Matter is basically anything that has mass and takes up space. So we are surrounded by countless amounts of matter. So non-scientifically speaking, matter is pretty much just stuff. Now, an element is a chemical substance that cannot be broken down to another substance. So it's 100% pure. For example, if we're talking about oxygen atoms, we're only talking about 100% oxygen atoms. We're not talking about oxygen is made out of 90% oxygen atoms and 10% nitrogen atoms. We're talking about 100% oxygen atoms. So the key thing to know is that an element is 100% pure and it cannot be broken down to another substance with different properties. Now, a trace element is an element that is vital for the organism, but the element's only needed in tiny quantities. So the organism still needs the element to survive, but in only small quantities. Now, a half-life is basically the time it takes for 50% of a substance or element to decay. A dalton is basically the unit of measurement of atomic and subatomic particles. Subatomic particles are as protons, neutrons, and electrons, and I'll explain those terms later in this video. Now, compounds are basically the combination of two or more elements chemically bonded together, such as sodium chloride or table salt. Table salt is consisted of two elements, sodium and chlorine, ionically bonded together. And I'll explain what an ionic bond is later in this video. But the key thing to observe here is that a compound is two or more elements chemically combined together. And they're different from elements because one, they consist of two or more elements, and then two, because they consist of two or more elements, they are not 100% pure. So I will show you a picture of each thing that we discussed. So let's go on Safari and let's see if we can find any good. So elements diagram. So now, okay, so let's see if we can find something that's good. Alright, this is good. So as you can see in picture A, that represents an element because it's 100% pure. Well, those basically represent molecules of elements because molecules are simply two or more atoms chemically bonded together. But as you can see, A is consisted of elements of an element because, or molecular elements because it's only consisted of one thing, meaning it's 100% pure. Similarly, B is basically the same thing, two or more atoms. That means that this is consisted of molecular elements. So basically, you can tell that it's an element because it's only consisted of one thing. It's 100% pure. Now for C, you can tell that it's a compound because it's consisted of two or more elements chemically bonded together. Now, for D, you can tell that there are different compounds they're different compounds being mixed together. So you can tell that picture D is a mixture because there's different compounds mixed up. But don't really worry about mixture definitions. But as you can see, it's simply just different compounds. So those are pictures, and you can see more over here. And yes, not that difficult. So you can even see this one. And yeah. Oh, not this one. Alright. Now, atoms are basically the smallest unit of matter that still retains an element's properties. So, What you need to know is that the most center point of an atom is called the nucleus, and it's consisted of subatomic particles called protons and neutrons. And so basically, and then electrons rapidly spin around the atomic nucleus, creating a cloud of negative charge. And we'll explain subatomic particles after we explain atoms, but let me show you a picture of an atom. So this should be a picture of an atom. So as you can see in this picture, the nucleus is simply consisted of protons and neutrons, and then the electrons simply spin around the nucleus and create a negative charge. A negative cloud, I should say. Now, protons, as we mentioned, basically are subatomic particles that have positive charge, and neutrons have neutral charge, and electrons have negative charge. Now, the key thing, the really important thing to note here is that protons and neutrons are almost identical in size. They're roughly 1 Dalton, and electrons are significantly smaller. In fact, they're so minuscule that when we calculate the mass number, we completely ignore them because of their minuscule size. And even if you went back to the diagram, you could see how significantly smaller that the electrons were to the protons and neutrons. Now, this picture is obviously not drawn to scale, but it still shows that the electrons are much smaller than the protons and neutrons. And if you want to be exact here, an electron is about 1 out of 1835 Daltons. So protons and neutrons are roughly, if you rounded it to the nearest thousandths, 2,000 times bigger than an electron. So all you need to know is the significance of the size and the charge of the subatomic particle. Now, basically, radioactive decay is basically when the atomic nuclei is unstable, so it starts to decay or lose subatomic particles from its nuclei, and then because of this loss of particles, it results into energy. Now, do note that radioactive decay can turn other elements into other elements, but we won't cover that because we're only covering basic chemistry. Because then again, this is a biology textbook, not a chemistry textbook, so don't expect too advanced topics here. We're just covering and touching some key terminologies. Now, the atomic number is basically the amount of protons in an element. So for example, let's pull up a periodic table. So if we pull up a periodic table, if you go on Wikipedia and we zoom in on this periodic table, we can see that the atomic number are simply above the chemical notation for that element. And so basically atomic number basically defines how many protons are in an element. So basically the number of protons or the atomic number defines the element. For example, oxygen has 8 protons and fluorine has 9 protons, but even though they differ by 1 proton, they're still different elements because they have different protons or different amount of protons, thus different atomic numbers. So all you need to know is that atomic number is equal to number of protons, and it defines an element. Now, okay, so mass number is basically the sum of the number of protons and neutrons in an element, and it's measured in Daltons. Note that the atomic mass / weight number is not, I shouldn't say roughly equal to, but note that the atomic weight number is a more specific number than the mass number. So basically the mass number is just a rounded version of an atomic mass number. So remember when I said protons and neutrons were roughly 1 Dalton? That doesn't mean they're 1 Dalton. That means they're extremely close to 1 Dalton. So basically the mass number ignores this closeness and basically just approximates it. So for example, in oxygen, the mass number is 16 because there's 8 protons and 8 neutrons, but the atomic weight is 15.9994 because it accounts for the size being a little bit less than a Dalton. So all you really need to know is that the mass number is simply the rounded version of the atomic weight, and you calculate this by summing the amount of protons and neutrons. Now, isotopes are essentially elements with the same amount of protons but different amount of neutrons. So, for example, carbon has 3 types of isotopes: carbon 12, which is the most popular by 99%, carbon 13, which is the second most popular, and carbon 14, which is the third most popular, so the least most popular. So basically, as you can see, they're isotopes because they have different atomic numbers. So if they have different atomic numbers, we note that we define an element by the amount of protons. So we note that isotopes must have the same amount of protons but different neutrons because they have different mass numbers, because the mass number is equal to protons plus neutrons. So as you can see, they're just elements with different atomic numbers, thus different number of neutrons. So an important note is basically the atomic weight. If an element has more than one isotope, such as carbon, then to find the atomic weight, you simply average all the isotopes together. Now, electron shells are basically regions that are made by concentric circles of an atom. Now, the concentric circles are just circles that have the same center. Now, in this case, the nucleus is the shared center. And basically, these electron shells determine the respective energy of an electron. The further shells have higher energy, and the closer shells have lower energy. Now, let's pull up a picture of an electron shell so I can show you what I mean. Hopefully, we don't get too. Now, here we have sodium, right? Do not worry about the configuration, just I want you to see, as you can see, that the nucleus is obviously in the middle, and as you can see, the regions are basically over here. So the regions are made by the concentric circles, and so basically, if an electron is further in a further shell, then it has higher amount of energy. But if it's in a closer shell, then it has lower amounts of energy. And the reason for this is because we basically define energy as the amount of work it takes to do something. Well, since we know that the nucleus has a positive charge, ignoring the neutron's charge because it's neutral, so since we know that the nucleus has a positive charge and the electrons have a negative charge, then we know that they will attract to each other because unlike forces or unlike charges attract. So if an electron's further out, then it obviously takes more work to push it further out because they already attract due to unlike forces. Conversely, with closer elements, it's obviously easier for us to put it closer together because they obviously attract. Now, valence shells are basically the outermost shell in an atom. For this reason, they have the highest amount of energy. Now, incomplete shells are reactive and complete shells are unreactive. So the reason for this is because elements try to fill their valence shell. In other words, they try to get the maximum capacity for their outermost shell. So if an element has an incomplete shell, then it will want to react with other elements in order to complete its shell. And basically, if the element already has a complete shell or already has a complete valence shell, I should probably say incomplete valence shells, but if it already has a complete valence shell, then there's no need to react with other elements because elements only react when they want to fill their valence shell, or in other cases, but that's usually what happens. And we'll explain this in a little bit more in covalent and ionic bonds. Now, orbitals are basically three-dimensional shapes that are components of electron shells. So electron shells, once again, are just regions made by concentric circles. And so basically, these orbitals are basically not where an electron spends 90% of their time in. Now, no more than 2 electrons in each orbital. So, for example, I'll pull up a picture of an orbital. Now, do not worry about types of orbital because this is just simple chemistry. In fact, I can't wait till we get to Unit 3. That's more interesting, to be honest. Okay, so in fact, don't even worry about that. It's a little bit advanced, so let's not worry about the diagram. But all you need to know is that no more than 2 electrons in each orbital, and they're just three-dimensional shapes, and 90% of the time. That's all you need to know for this chapter. Now, covalent bonds are basically when two atoms share pairs of electrons to complete their valence shell. So basically, single bonds means they only share one pair of electrons, and double bonds means they not equal, not plus. It should be equal. So, and double bonds mean two pairs of electrons. So, for example, let's pull up the periodic table. Now, hydrogen might want to bond with a halogen, and the reason for this might want to covalently bond. So, assuming that hydrogen is neutral, assuming that hydrogen is neutral, so let's just zoom in on this. In fact, I will just take a picture of this and zoom on here. So, hydrogen might want to bond with a halogen. Now, a halogen has 7 valence electrons, and a hydrogen has 1. Now, hydrogen needs one more valence electron to essentially complete the first valence, to complete its valence shell, and fluorine needs 1 to complete its valence shell. So they might share an electron in order to complete both of their valence shells. So essentially, all you need to know is that atoms covalently bond together in order to share electrons, thus so they can complete their valence shell. Also, if you want to know how many electrons per shell, it's simply 2 plus 6 plus 8 plus 10 ... So 2 in the first shell, then 8 in the second shell, 18 in the third shell, and 30 in the fourth shell, and you simply do this. So it's basically a series, so it's not that complicated, but don't really worry about it. That wasn't actually in the textbook, but that's if you want to know. The textbook doesn't really go that advanced, to be honest. Now, electronegativity is basically the force or attraction of valence electrons to an element. For example, fluorine is the most electronegative element, so basically that means that it basically just hogs all the electrons, or hogs all the valence electrons, and basically oxygen is the second most electronegative element. So basically all you really need to know is that electronegativity is a force or attraction of valence electrons to an element. Now, polar bonds are basically covalent bonds that have different electronegativity. Do not worry about the thing in parentheses. Do not worry about that stuff. But basically, another way to view polar bonds is they're covalent bonds with a partial positive N and a partial negative N. But the key thing is that in H2O, right, H2O is a polar bond. Water is obviously polar because oxygen is significantly more electronegative than hydrogen. So oxygen, basically the electrons face towards oxygen rather than hydrogen. So because they have a vast difference of electronegativity, they're polar. And polar bonds will be more explained in chapter 3 in the mention of hydrogen bonds and all that stuff. Cool stuff. Now, non-polar bonds are basically covalent bonds with atoms that have roughly the same negativity. So, such as oil, or let's say carbon and hydrogen, right? CH is a non-polar bond because they equally share the electrons, meaning that they roughly have the same electronegativity. So basically, you just need to know those two facts. And in fact, I'm not going to go too deep into this because in the next overview in chapter 3, I'll be going more deep and more advanced in that topic because chapter 3 does explain it more advanced. Now, an ion is basically an atom with a different amount of electrons and protons. Now, a cation is a positively charged atom, so an atom with less electrons than protons, because since it has more protons, it has more of a positive charge, so it's a cation. And then anions are basically a negatively charged ion, so atoms with more electrons than protons. So since it has more electrons, then it has more of a negative charge. So that's pretty simple. And don't worry, ions will be explained more in chapter 3. A lot of the stuff are explained better in chapter 3 in my opinion. I think they really should have just condensed chapter 2 and 3, but it's fine. Ionic bonds are basically bonds between two ions. Now, when an element is significantly more electronegative than an element, it just strips the electron from the element. So in other words, when two atoms transfer electrons between each other. So basically, you just need to know there are bonds between atoms, and basically they transfer electrons between each other. Like I said, we will go more advanced in the next video. Now, hydrogen bonds are basically and also I recommend you watch a video on Khan Academy on the last three terms, because I'm not going to go too advanced on them because the book did not go too advanced, and this is an overview of the book. But hydrogen bonds get explained a lot better in chapter 3. In fact, they are a reoccurring idea in chapter 3, and they're very important in chapter 3. So in chapter 3, you will understand hydrogen bonds a lot more. But all you need to know for chapter 2 is that hydrogen bonds are weak bonds between a hydrogen with a partial positive charge and an electronegative atom with a partial negative charge. For example, H2O is a hydrogen bond because hydrogen has one region of partial positive charge, and an oxygen has two regions of partial negative charge, and due to this definition, they're obviously hydrogen bonds. Now, van der Waals are basically weak bonds that happen between atoms with transiently changing charges. So basically, bonds that happen with atoms that are close. Now, I do recommend you go on Khan Academy and you watch a video on this, because actually, this type of bond is not really explained that well in Campbell's, and I obviously would understand that because it's a biology textbook, so it's not meant for chemistry. Now, chemical equilibrium is basically when the forward and reverse reaction rates are equal or unchanged concentration of reactants and products over time. And I do recommend for the last one you watch a video on that. So the last three terms, do not worry about them too much, especially for hydrogen bonds, because we will be covering hydrogen bonds a lot more in chapter 3. And yes, thank you for this video. And stay tuned for chapter 3. And like I said, I'm not going over the questions because I want to leave that as an exercise for y'all, and some people have different editions anyway.